Well, in this section we want to cover comets in the Oort Cloud. And this is a beautiful picture of comet. It's a little bit enhanced, but it gives you an idea of what some comets look like. And they typically have this long tail, and they are actually coming into our solar system from usually way out in the Oort Cloud. And that's what this section is going to be about, how we know what we know about comets. So let's go see this this particular image. It's of Halley's Comet. And Halley's Comet was discovered by Edmund Halley. And it wasn't discovered by Edmund Halley, but Edmund Halley was the first one to recognize that it was on some sort of period of 75 to 76 days, years, so that we could expect it to come back in. And of course he hypothesized that it must be on some sort of orbit, and indeed we've now made measurements and we've discovered that Halley's Comet is on an elliptical orbit, which a very big orbit, which brings it back around every 75 or 76 years. It's due to be back in 2062. Let's go back to that original diagram, because there's a lot of things to talk about there. The first thing I want to talk about is the fact that we do not see comets until they get within about 3 AU. Remember AU being 1 Earth distance. 1 AU is 1 Earth distance, so therefore we're looking at 3 AUs, 3 Earth distances. The comets, we don't see them until they get within about 3 AU, and that's because the temperatures from the solar wind when the comets come in, and as you can see there, the comets consist of ices, primarily water, but they also have ammonia, methane, carbon dioxide, and carbon monoxide in them. So we wouldn't see a comet because they're too small, and the only reason we do see them is because when the solar wind strikes them, the comets, they will heat up and water will sublimate at about water sublimates at about 162 degrees or so, and then you'll form this coma. It's a kind of a gaseous thing that surrounds the comet, and it reflects sunlight, and that's the only reason that we see these comets coming in. So we really have to wait until about 3 AU till they get within the inner solar system before we even begin to see them. Now the coma is made up of, I should say the comet is made up of these ices, but it also has particles in it too, dust particles. And the tail that's being generated from the solar wind hitting and striking the comet sends mostly these gases off into space, and it breaks down the ices into various compounds which are called radicals. And those compounds you see there given CH, NH2, CN, C2, C3, and these compounds are called radicals because they radically react, if you want to know the truth, with other compounds in Earth's atmosphere. So those are not stable in Earth's atmosphere. They can only be stable in a place like space. They would readily react in our atmosphere, and that is an important thing to know about comets. The other important thing I think that I should emphasize with you is that a comet, when it goes around the sun, we tend to automatically think that the tail is going to be opposite direction as the way the comet moves. But as you can see in this diagram in the upper left part of the slide, you don't have that at all. In fact, the tails are actually parallel with the motion of the solar wind. When the solar wind strikes the front of the comet, of course the tails are taken off in the opposite direction, and the material. And in fact, if you look down at the comet in the picture, the comet seems to be spreading out the further away you go out on the tail. And that's because of the orbit of the comet. You can see in the smaller diagram how the dust trails will actually get spread out because the comet is moving in a direction different than the tail does. And again, that explains why not only we have the tails moving away from the sun, but also how they get spread out because of the motion or the orbit of the comets. Now, in general, comets have very large orbits, and I want to tell you a little bit about some of the first discoveries that were made with comets. In 1950, two very important papers were done. One was by Fred Whipple, and he used a very famous phrase now. He called these comets dirty snowballs. And the reason he said that was that they're made up of dust, and they're made up of ices. And so I think dirty snowballs is a good way to describe them. He also recognized that comets wobble a little bit or move a little bit in their orbits. They change orbit. And he suggested that maybe when the solar winds are hitting the ices on the comet, that the ices get sublimated and it concentrates dust particles, or the particles that I mentioned in the dirty snowball name. Those particles get concentrated on the surface of the comet, and therefore they keep the gases from escaping on a regular basis. They get trapped underneath the surface of these particles. And then when the pressures build up great enough, the gases will escape and they'll shoot out like a jet, and it will force the comet into a slightly different orbit. And thus that explained or it explained why we have the changes in the orbits of the comets as they go around the sun. So some really superb work done by Fred Whipple. And in the 1950s, as we'll talk about in a minute, we also had some important work done by Jan Oort. Let's take a look at this diagram to give you some idea of where we find the Oort Cloud, which is believed to be the source of the comets. The Oort Cloud, first of all, this scale is logarithmic. So you're looking at the planets in the interior, and as you go out, it's really getting farther and farther distances away. And the Oort Cloud seems to start somewhere around 1,000 on this diagram, and these are in AUs again, and it goes all the way out to about 200,000 AU. And these are way outside the Kuiper belt. They're way out there. To give you some idea, look at where Alpha Centauri is. Alpha Centauri is 4.37 light years away from us here. And so an immense amount of distances that we still see Oort Cloud. The Oort Cloud are these comets. They're the dirty snowballs that Whipple talked about. And they are gently rotating. Some of them are in these immense orbits, but this cloud is locked to the sun's gravitational pull. And of course, the farther away you get, the easier these comets get to be, or knocked out of the Oort Cloud and sent off into space. Most of the time towards, not most of the time, but a lot of the times towards sun. So that's how you develop these orbital orbits that we see in the comets that come into our solar system. And that's kind of important. You get a situation then where you have two different types of comets. You have the comets that are within the plane of the solar system. So they would be in this plane that we're looking at right here. And they circle the sun within that plane, and there seems to be a concentration of them within that plane. But there's also a spherical group of comets that are completely around the sun, and oftentimes comets will come in from that group, and they're called the isotropic comets. The other type of comet within the plane, those are called the Jupiter family comets. They're affected by Jupiter. I won't go into the details. It's quite complicated. Anyway, the idea here is that we have these two separate types or groups of comets. The main thing, though, to stress here is that we have this spherical cloud called the Oort Cloud, and I'll talk about how Jan Oort proposed that in just a minute. I want to also mention in this diagram that the isotropic comets and the Jupiter comets are in this huge orbits, but sometimes comets can just be coming through and passing through the solar system. So some star may be passing by our solar system, not too close, but enough to jostle these comets out in the Oort cloud and send them off in different directions. And sometimes they'll come through and they'll be picked up by the sun gravitationally and Jupiter and those other planets, or they can pass on through and never be seen. Well, let's take a look now at this diagram. This is kind of an interesting one in terms of grouping the comets that we know of. First of all, on the y-axis, that's the number of comets, and on the x-axis is the semi-major axis in AU. If you recall, the semi-major axis, every elliptical orbit has a large diameter. We call that the major diameter. And if we cut that in half of the major diameter is called the semi-major axis. So the semi-major axis is what you're looking at. If you want to know the true diameter of the orbit, the largest diameter of that elliptical orbit of any of these, you'd have to multiply by 2. So something that has an AU, a semi-major axis of 30,000 AU, is going to actually travel 60,000 AU, or a diameter of 60,000 AU, around our sun. Well, we group the group here that we call the returning comets. You can see that the cutoff's about 10,000 there. The ones that are closer to the sun, those are believed to be perturbed by the giant planets, and they come from the new comets that you see to the right there, between 10 and 100,000. So the new comets seem to be the source of the returning comets, and the comets that we see that we call new, these are ones that seem to be on an orbit that has been in a stable part of the sky, that is in the Oort cloud. I didn't mean the sky, but outside of our solar system. So we think that the Oort cloud consists of this area of stability for these comets. No one's ever seen the Oort cloud, but we postulate, based on the new comets, that there is all this material out there, and some of this material is coming in from the Oort cloud and orbiting on these very long elliptical orbits. I mean, these are huge elliptical orbits. When you start talking about 10,000 and on up, that's huge. In fact, one 30,000 AU semi-major axis, it would take about 5 million years for that comet to go around the sun. And here's the thing: we don't think that something can be stable for the billions of years that our solar system has existed, continually going around the sun on these huge elliptical orbits for 5 billion years. There are bound to be things that they'll run into, or that they'll be affected by passing stars. Even the gravitational pull of the galactic center can affect these things. So that's why we think that there's a cloud out there, because these things probably, these large orbiting comets probably are unstable and would not orbit continuously over the 4.5 billion years of the solar system, 4.56 billion years that the solar system's existed. So it's natural then to assume that there's a lot more out there, and that these comets are just being pulled in periodically by passing stars and being grabbed up by the sun. It's complex, but we think that there's a lot of material out there that has not. Now, the big question is, where did that material come from? And that's where Jan Oort comes into play. He did a very famous paper, there he is right there, in 1950, and Oort postulated that there was, at one time, the comets were evenly distributed. These gaseous, or I should say these icy, dirty particles, were evenly distributed throughout our protoplanetary disk. We'll talk a lot more about that a little bit later on. And then anything within 3 AU is going to be sublimated away, so we don't have to worry about that. So we're talking about somewhere between 4 AU out to 30 AU or so of our solar system. All those are going to, it turns out, if we do modeling, they're going to be perturbed and they're going to be kicked out of our solar system and thrown out into a stable area where we think the Oort cloud exists, where I showed you before. So probably all of the material that's in the Oort cloud came from our solar system, and or it should say what we typically term the solar system, that is from Neptune inward, or even the Kuiper belt inward. And so that material is unstable, it gets thrown out into the Oort cloud, and that's why we have the Oort cloud existing out there. And that idea was first postulated by Jan Oort. And so there's a lot of gravitational interaction that went on that created instabilities for this material, and it sent them on out. Now this is kind of an interesting photograph that I've included here because we wanted to know and study comets over the last few decades, and so we sent out a space probe, and that space probe was called the Rosetta spacecraft, and we sent it to study the comet Philae. And Philae had the space probe had a lander that went down and landed on Philae, and you may have heard the news when it hit, it bounced around and finally settled down, unfortunately, next to a cliff, and the cliff has prevented the lander from getting enough sunlight to function all year round. So we're limited in the amount of data that it's returning. It still gets enough energy, but we have to wait much longer for the batteries to recharge. And this is one image that has been sent back by Philae. And the comet is 67P, in case you're interested in those kinds of things.